Hi, this is Mark Weitzman. Welcome back to my channel on topics, my YouTube channel, Theoretical Physics with Mark Weitzman. This would correspond to a topics in theoretical physics on my Piazza site. So today I want to just do a problem from David Tong's Classical Electromagnetism book, which just came out recently. He has 4 books that just came out. I'm working through most of the first and second books, and I'm going to try and do the next couple of books in the next month or so. He's got exercises for the problems right on the website for the book. And so he has, like, this is his example sheet too for magnostatics. And I'm going to do problem 3 today. I'll show you a little more of a close-up. So the problem is a steady current flows in the z direction uniformly in the region between the cylinders x squared plus y squared equal a squared. And let me draw this. And another cylinder which is offset from it, x plus d squared plus y squared equal b squared, where b is the outside cylinder and a is the inside cylinder. And the offset is between them, not in the annulus, but in the A cylinder. That's what this inequality means. And it says, show that the associated magnetic field throughout the region x squared plus y squared less than a squared is given by this expression. So let's get to work. And so what we have is let me just problem 3, example sheet 2. David Tong, electromagnetism. Now, this isn't a difficult problem. I would say it could be considered a first-year physics problem, or a maybe a second year, but it's certainly capable of being done by freshman students. So what we have is, and excuse my horrible drawing abilities here, but let me try it. What we have is a cylinder, an inside cylinder. And then we have another cylinder which is like offset from it, but not symmetrically. That was a horrible job, but the inside cylinder has radius A. And the amount of the offset, which is the radius, the center for the outside cylinder, is D. And the whole thing from there to there is B. And there's a current between these two cylinders. I'll just shade it. There's a constant current density. We're considering these things as like in a vacuum, so you don't have to worry about the effects of any materials. So there's a constant current density in the annulus between the cylinders. And this leads to a current I. So it's a steady implies that there's a steady current I between the cylinders. Okay. And so that's what we have. That's the setup. And I should say it's in the z direction. And the directions here are like X is this way and Y is this way. And Z is coming out of the page upwards. And, okay. So, it's not completely obvious how to solve this. We can try and use Ampere's law, but there's no symmetry here, as you can see, because the cylinders are offset from the centers of one another. So you're not going to be able to use Ampere's law to solve it directly, but you can use Ampere's law to solve it. And the key is to use just use the principle of superposition. So imagine that we have a uniform current I in the interior of the outer cylinder with radius B, comma. Now this will also give us a current in the interior, but we don't want a current in the interior of the cylinder A, so we have to imagine also combined with a current in the minus Z direction in the interior of the inner cylinder with radius A. So when you do both of them, you'll end up getting the problem that you want. So we just need to solve each problem separately. Now, from problem 2, so I'll give a brief derivation in a second. From problem 2 on the example sheet 2, Ampere's law with the symmetry gives the gives in the interior of a cylinder with radius R the magnetic field is given by B is equal to, and unfortunately I'm using MKS units, but that's what the book, Tong's book, uses. U0 to R. R is the radius from the center of the cylinder to the point in the interior. So what you have is a cylinder of radius R, and we have a point that's R away from the let's add a mu0 over 2 R J, and then there's a current J, current density J times, this is in polar coordinates, so you could think about here phi caret would be this way. It's just polar coordinates. So that would be the vector. The magnetic field goes around. In the right-hand sense, it goes around counterclockwise because the current is coming outside of the page. And so J J is equal to why won't it? I hate when it does this to me. Okay. J is equal to I z caret over pi r squared. Okay, so that's the result of problem 2. Now we're going to apply that to each of the cylinders. The outer cylinder will have a positive current going up, and the inner cylinder will have a positive current going down. So first thing I would like to write is that what is the current density? The current density is going to be the same everywhere where it's non-zero, but this is just equal to the current in the z direction divided by pi b squared minus a squared, because the area, this whole thing is just the area of the annulus. And this is going to be, this is the current density J in the annulus. And then J in the interior of, J is equal to the same magnitude, but it's the opposite direction, minus I z hat pi b squared minus a squared. This is in the interior of the inner cylinder. So we now have our currents, and we can apply our formula for the magnetic field. I just want to do the brief derivation. Of the box formula, I'll call it asterisk. And it's simply the magnetic field, the line integral around the radius of the circle is equal to mu 0 times the current through that surface that surrounds that line integral, which is just pi r squared times the current density J. So this implies that B is equal to mu 0 over 2 R J phi hat. Okay, so that's just Ampere's law. Now let's this is easy. It seems like you should proceed in polar coordinates, but actually it'll get messy. I think it's easier if you proceed in rectangular coordinates. So let's use rectangular coordinates, and we'll use x, y, z for the inner cylinder, and x prime, y prime, z prime for the outer cylinder. And these are related very simply by x prime is equal to x plus d, y prime is equal to y, z prime is equal to z. And additionally, we have the unit angular polar coordinate vector. And this is just given by minus y over r. R is just the square root of x squared plus y squared times ex plus x over the square root of x squared plus y squared times ey. Now, if you don't remember this, the easy way to get it to do a quick check is, let's say we're at 0, 0. Let's say we're at, I'm sorry, not 0, 0. Let's say we're at a coordinate given by, a polar coordinate given by r comma theta equals 0. Then we know, so we're at a circle here, and we're at this point here. We know that the phi is that way, so we should get ey for the unit vector. Let's see if it works. Here we have y is 0, so this term goes away, and x is just r, the same in the denominator r, so it's ey, so that's correct. And then if you do like r comma theta equal pi over 2, now we're over here, so we should get phi hat equals minus ex. And as you can see, at theta equals pi over 2, we have x equals 0, so this second term vanishes, but the first term is just minus 1, so that works out correctly. So anyway, now phi prime is different because it's at a different origin. Relative to the coordinates at the for the outer cylinder, it's also the same formula, minus y prime ex prime square root of x prime squared plus y prime squared. Then I have plus x prime over the square root of x prime squared plus y prime squared times ey prime. The e's don't change because unit vectors and rectangular coordinates don't change under a translation. So they're the same. And so this is just equal to, we can write it in terms of our inner cylinder coordinates using this coordinate transformation above. This is just equal to minus y ex caret over the square root of x plus d squared plus y squared plus x plus d is x times ey hat over the square root of x plus d squared plus y squared. Okay, so now we can actually do the actual calculation. The magnetic field B is equal to 1/2 mu 0 times J. We're going to do the outer cylinder first. J is in the upward direction. So that would be Z hat times R, and R for the outer cylinder would just be x prime squared plus y prime squared times phi hat prime minus for the inner cylinder 1/2 mu 0. The current density is the same but the opposite direction. That's why we have this minus sign times the square root of, we'll use the coordinates on the inner cylinder, x squared plus y squared phi hat. Okay, and this is equal to 1/2 mu 0 J okay. I'm sorry, I shouldn't have the Z hat there. 1/2 mu 0 J times the square root times the square root of x plus d squared plus y squared times, we'll substitute this over here, minus y over the square root of x plus d squared plus y squared dx plus x plus d over the square root x plus d squared plus y squared ey hat. And then doing the inner cylinder, we get minus 1/2 mu 0 j the square root of x squared plus y squared times minus y ex over the square root of x squared plus y squared plus x ey square root x squared plus y squared. Okay, and you can see the beautiful thing is that this cancels this, and this cancels that and that. So that's why this works out so easily. So we get minus 1/2, plus 1/2. 1/2 b equals 1/2 mu 0. I'm going to substitute for j, I, hold on one second. I divided by pi times b squared minus a squared. And then what we're left in from these two expressions here is just minus y ex hat plus x plus d ey hat plus y ex hat minus x ey hat. And as you can see, we get some nice, beautiful cancellations. This term cancels with this term. This term cancels with this term. And we're just left with b equals mu 0 I 2 pi b squared minus a squared d and ey hat. And that is our answer. It's a real nice answer. The magnetic field is just in the y direction, and it works out very nice. So that's the solution to the problem. Now, I was curious after I did this. I went to Chat GPT, and I'll put a link underneath the description on the video. And so I went to Chat GPT, and this isn't exactly what I typed in. I typed it in a little more correctly the first time. I had the correct a squared there, but let's just read what I wrote. I tried to copy paste, but it didn't get it right. So, a steady current I flows in the d direction uniformly in the region between the cylinders x squared plus y squared. I didn't put what it was. I accidentally left out the equals a squared. And x plus d squared plus y squared equal b squared, where 0 is less than d is less than b minus a. What is the associated magnetic field throughout the region x squared plus y squared is less than? I did put in the 2 there, so a squared. Now, it's thought for a second, and it completely interpreted the problem correctly. It figured out that x squared plus y squared is a squared, and that's the inner cylinder, and then there's a cylinder outside of that, and the region, magnetic field in the region in the inner cylinder. And did the correct physical interpretation, no problem. Ampere's law it did correctly, no problem. The consequence it did right. And it has a circulation, has the right equations. It points out the boundary conditions. It doesn't... It points out that the outer and inner cylinders are not concentric, since the outer one is offset by d inside the inner cylinder. The magnetic field must still be uniform to lowest order. I'm not sure about that. That's true, but that's not relevant. So it now works by analogy with an electrostatic problem where it must have had the solution on the web. And so it tries to work it out by analogy with the electrostatic. Of course, the electrostatic will have the different directions and everything, and it doesn't take that into account, and it gives this as the answer. It has it in the x caret direction, which might be right for electrostatics, but is wrong for magnetostatics. And it's missing a 2 pi there, probably because it's, I don't know why it's missing that 2 pi. Maybe the geometry 2 pi r and so on. But anyway, so it gives this as its final answer. So completely wrong. It then asked me if I wanted to use the vector potential approach, solving Laplace's equation with boundary conditions. I didn't do that. I decided to tell it what the answer was. I told it the answer is incorrect. First, by using superposition, you can get the exact result. Second, you're missing a factor 2. Finally, the direction of the field is in the y direction. I shouldn't have told it the direction. I should have just said it's not in the x direction. So now it apparently thought for 34 seconds, tells me I'm right. Now it does the completely correct derivation that I sort of led it to, which it should have gotten at first, and it gets the correct answer. So I'm kind of surprised, not surprised, but given all the hype about Chat GPT and how well, how they solve all these things now and everything, you would think it would have gotten it correctly, completely correct on the first try. And basically I had to guide it to the correct answer. It can do problems that are much harder than this, so I was surprised it had trouble with what is essentially a freshman sophomore physics problem. Anyway, thank you for watching, and I'll post some more videos on my quantum field theory chapter on scattering sometime in the next few days. I'll see you soon. Bye-bye.